Learning Objective 7 from Section 3.5 is to test a claim about the value of a population proportion using hypothesis testing, including checking requirements, writing hypotheses in words and in symbols, finding the test statistic, computing the p-value, and drawing the associated distribution, and writing appropriate conclusions. The owner of Dan's Health Foods is wondering if his customers' daily vitamin supplement habits are in the same proportion as the general population of adults. The shop owner heard in a new report that 60% of all adults reported that they took a daily vitamin. The shop owner believes that his customers have a greater proportion of adults who take a daily vitamin, so he decides to conduct a hypothesis test. The shop owner collected data from 50 randomly selected customers. Among these, 32 reported that they take a daily vitamin. Test the owner's hypothesis using alpha equals 0.01. Part 1. Using both correct statistical notation and words, state the null and alternative hypotheses. So the null hypothesis is written with an H sub 0, and we use the symbol P, which represents the population proportion, and there's an equal in the null hypothesis, and the claim proportion is the value from the report, which is 0.6. In words, we would write this as the proportion of the population, which in this case is all Dan's Health Food customers, who take a daily vitamin is equal to 0.6. Let's write the alternative hypothesis. The alternative hypothesis is written with an H subscript A, still about the population proportion P, but now the shop owner believes that his customers have a greater proportion, so we'll do a greater than 0.6. In words, this is saying that the proportion of the population that take a daily vitamin is greater than 0.6. So the proportion of all Dan's Health Food customers who take a daily vitamin is greater than 0.6. Report the test statistic rounded to 2 decimals. We're going to do this in GeoGebra. I've opened a probability calculator, and I'm in the Statistics tab, and I've selected the z-test of a proportion. The claimed p that goes in the null hypothesis is 0.6. We have a greater than, so I'll highlight that button. The number of successes were the 32 individuals who take a daily vitamin out of my sample size of 50. My test statistic is given to me right here in the output as the z. So it is 0.58 rounded to 2 decimal places. Next, report the p-value rounded to 4 decimal places, including drawing, labeling, and shading the appropriate distribution to show the p-value and test statistic. The GeoGebra output gives us the p-value. It's 0.2819 rounded to 4 decimal places. Let me draw the picture of what's going on here. The z distribution is centered around 0, and so a test statistic of 0.58 would be right here. That shows us the results of our test. The p-value is the probability of these results, or more extreme. We computed these values under the assumption that the null hypothesis was true, and that's part of the p-value definition as well. So more extreme is further in the tail, so I'm going to shade that. And that area right there is the p-value, which is equal to 0. Let me check it again, 2819. We compare this p-value to our alpha. Our alpha was 0.01. Our p-value is greater than alpha. So when the p-value is larger than alpha, that means we failed to reject the null hypothesis. In other words, the results that we saw were not unusual under the assumption that the null hypothesis is true. So there's no reason for us to fail to reject the null hypothesis. Do the data support the shop owner's hypothesis? Answer with complete sentences in context of the situation. So, since our p-value was greater than our alpha, then we do not reject the null hypothesis, and we do not have sufficient evidence to conclude that the alternative is true. The alternative hypothesis that the proportion of Dan's customers who take a daily vitamin is greater than 0.6 we do not have enough evidence to support that. That was the shop owner's claim or his hypothesis. So since the p-value is greater than alpha equals 0.01, there is insufficient evidence to conclude that the proportion of his customers taking a daily vitamin is greater than 60%. So no, the data do not support the shop owner's hypothesis. Let's do a second example. A cereal company claims that 25% of its boxes have a collectible prize inside, but a researcher suspects that the proportion is smaller. A simple random sample of 100 boxes is taken from all cereal boxes the company produces, and 18 of the sampled boxes had a collectible prize inside. Let's write the hypotheses. The null hypothesis is that P equals this claim proportion of 0.25, and the alternative hypothesis is that P is smaller. Here's where it says that in the question. So less than 0.25. One-tailed tests have either a less than or a greater than in the alternative hypothesis. Two-tailed tests have a not equal to in the alternative hypothesis. So in part 2, where we're asked if this is a one-tailed or two-tailed test, the answer is that this is a one-tailed test. In order to perform a one proportion z-test, the following conditions must be met. The sample must be a simple random sample. That was given to us. The sample values must be independent from each other. We checked that by verifying that the sample size is less than 5% of the population size. We had a sample size of 100 boxes. It's reasonable to assume that that is less than 5% of all the boxes produced by the cereal company. The conditions n times p sub 0 greater than or equal to 10 and n times 1 minus p sub 0 greater than or equal to 10 must be satisfied. Verify condition number 3 by showing the computations. So I need to compute n times p sub 0. Our n was our sample size, which was 100 boxes. The p sub 0 is the number in the proportion. So in that null hypothesis, we see that p equals 0.25. That's the value we use to check this condition. 100 times 0.25 is 25. That's above 10. And we'll also check n times 1 minus p sub 0. That is 100 times 1 minus 0.25, which is 100 times 0.75, which is 75. That's also above 10. So our conditions are met. So now we can report the standardized test statistic. Again, we'll do this in GeoGebra. I'm going to change my claim proportion to 25, my number of successes to the 18 boxes that had a prize inside, and my sample size to 100, the number of boxes I looked at. And here's my test statistic, negative 1.62. Rounded to 2 decimal places. And the p-value, rounded to 4 decimal places, is 0.947. Oops. I forgot to highlight the less than. My p-value was incorrect. This is an important thing to recognize. If you highlight the wrong inequality in GeoGebra, you'll get the wrong p-value. So as I wrote in my alternative hypothesis that I had a less than, I need to highlight the less than button. Now I have the correct p-value, which is 0.053 rounded to 2 decimal places. Sorry, rounded to 4 decimal places, so it's 0.0530. Let's interpret this p-value in context. If the proportion of boxes with a prize inside is, so the p-value is based on if the null hypothesis is true. Our null hypothesis stated that the proportion with prizes was 0.25. Then the probability of getting a sample with a sample proportion, well, what was our sample proportion? That was 18 divided by 100. So we had 18 successes divided by 100. That gives us a sample proportion of 0.18. Then the probability of that happening, or less, because that's or more extreme, is 0.0530. That's our p-value. Using a significance level of 0.1, do you reject or fail to reject? Well, now our p-value is less than our alpha of 0.1. If the p-value is lower than alpha, we reject the null hypothesis. A memory tool is p low, reject HO. And so then what conclusion can we draw? Well, our p-value is less than alpha, so therefore we have sufficient evidence to conclude that the alternative hypothesis is true. There is sufficient evidence to conclude that the proportion of all cereal boxes produced by the company that had a collectible prize inside is less than 25%.